In probability theory and statistics, the negative binomial distribution is a discrete probability distribution of the number of successes in a sequence of independent and identically distributed Bernoulli trials before a specified number of failures occurs. For example, if we define a 1 as failure, all non-1s as successes, and we throw a die repeatedly until the third time 1 appears, then the probability distribution of the number of non-1s that had appeared will be a negative binomial. The Pascal distribution and Poisson distribution are special cases of the negative binomial. There is a convention among engineers, climatologists, and others to reserve negative binomial, in a strict sense, or Pascal, for the case of an integer-valued stopping time parameter r, and a use Poisson for the real-valued case. For occurrences of contagious, discrete events, like tornado outbreaks, the Poisson distributions can be used to give more accurate models than the Poisson distribution by allowing the mean and variance to be different. Unlike the Poisson, contagious events have positively correlated occurrences causing a larger variance than if the occurrences were independent, due to a positive covariance term. Definition: suppose there is a sequence of independent Bernoulli trials, each trial having two potential outcomes called success and failure. In each trial the probability of success is p and of failure is. We are observing this sequence until her predefined number r of failures has occurred. Then the random number of successes we have seen, x, will have the negative binomial distribution. When applied to real-world problems, outcomes of success and failure may or may not be outcomes we ordinarily view as good and bad, respectively. Suppose we use the negative binomial distribution to model the number of days a certain machine works before it breaks down. In this case, success would be the result on a day when the machine worked properly, whereas a breakdown would be a failure. If we used the negative binomial distribution to model the number of goal attempts a sportsman makes before scoring our goals, though, then each unsuccessful attempt would be a success, and scoring a goal would be failure. If we are tossing a coin, then the negative binomial distribution can give the number of heads we are likely to encounter before we encounter a certain number of tails. In the probability mass function below, p is the probability of success, and is the probability of failure. Probability mass function. The probability mass function of the negative binomial distribution is here the quantity in parentheses is the binomial coefficient, and is equal to this quantity can alternatively be written in the following manner, explaining the name of negative binomial. To understand the above definition of the probability mass function, note that the probability for every specific sequence of k successes and r failures is rpk, because the outcomes of the k plus r trials are supposed to happen independently. Since the RTH failure comes last, it remains to choose the k trials with successes out of the remaining k plus r minus 1 trials. The above binomial coefficient, due to its combinatorial interpretation, gives precisely the number of all these sequences of length k plus r minus 1. The following recurrence relation holds. Expectation: the expected total number of trials k plus r of a negative binomial distribution with parameters is r. To see this intuitively, imagine the above experiment is performed many times. That is, a set of trials is performed until r failures are obtained, then another set of trials, and then another, etc. Write down the number of trials performed in each experiment. A, B, C, and set A plus B plus C plus equals n. Now we would expect about n failures in total. Say the experiment was performed n times. Then there are near failures in total. So we would expect near equals n, so n equals r. See that n is just the average number of trials per experiment. That is what we mean by expectation. The average number of successes per experiment is n-r, which must have expected value equal to r minus r equals rp. This agrees with the mean given in the box on the right-hand side of this page. Extension to real-valued r. It is possible to extend the definition of the negative binomial distribution to the case of a positive real parameter r, although it is impossible to visualize a non-integer number of failures. We can still formally define the distribution through its probability mass function. As before, we say that X has a negative binomial distribution if it has a probability mass function. Here R is a real, positive number. The binomial coefficient is then defined by the multiplicative formula and can also be rewritten using the gamma function. Note that by the binomial series and above, for every 0p less than 1, hence the terms of the probability mass function indeed add up to 1. Alternative formulations. Some textbooks may define the negative binomial distribution slightly differently from here. The most common variations are the definition where X is the total number of trials needed to get our failures, not simply the number of successes, since the total number of trials is equal to the number of successes plus the number of failures. This definition differs from ours by adding constant r. In order to convert formulas of this article into this alternative definition, replace everywhere k with k r, and also subtract r from the mean, the median, and the mode. In order to convert formulas written with this definition into the one used in the article, replace k with k plus r, and add r to the mean, the median and the mode. Effectively, this implies using the probability mass function, which perhaps resembles the binomial distribution more closely than the version above. Note that the arguments of the binomial coefficient have decremented due to order. The last failure must occur last, and so the other events have one fewer positions available when counting possible orderings. Note that this definition of the negative binomial distribution does not easily generalize to a positive, real parameter r. The definition where X is the number of k failures that occur for a given number of r successes. This gives a distribution for the number of failures instead of the number of successes. In order to convert the original formula of this article into this alternative definition, swap k and r everywhere, and the binomial coefficient will now be choosing k1 failures from the first k plus r1 trials. Effectively, this implies using the probability mass function where k is now the number of failures and r is now the number of successes. Alternatively, this formulation can also be written in terms of k failures and n trials by recognizing that n equals k plus r. The definition where p denotes the probability of a failure, not of a success. In order to convert formulas between this definition and the one used in the article, replace p with 1 minus p everywhere. Likewise, the corresponding text will have the words failure and success swapped compared with the original case. The previous condition can be combined simultaneously with an alternative definition of X, i.e., X counts total trials, and P is the probability of failure. In negative binomial regression, the distribution is specified in terms of its mean, m, which is then related to explanatory variables as in linear regression or other generalized linear models. The probability mass function then becomes the variance can then be written, and the parameter r is referred to as the dispersion parameter, shape parameter, or clustering coefficient, or the heterogeneity or aggregation parameter. The term aggregation is particularly used in ecology when describing counts of individual organisms. Decrease of the aggregation parameter r towards 0 corresponds to increasing aggregation of the organisms. Increase of r towards infinity corresponds to absence of aggregation, as can be described by Poisson regression. Some implementations of negative binomial regression use the reciprocal of R and refer to that also as the dispersion parameter. Sometimes the distribution is parameterized in terms of its mean mu and variance sigma 2. In that case, and occurrence waiting time in a Bernoulli process for the special case where R is an integer. The negative binomial distribution is known as the Pascal distribution. It is the probability distribution of a certain number of failures and successes in a series of independent and identically distributed Bernoulli trials. For K plus R Bernoulli trials with success probability P, the negative binomial gives the probability of K successes and R failures, with a failure on the last trial. In other words, the negative binomial distribution is the probability distribution of the number of successes before the RTH failure in a Bernoulli process, with probability P of successes on each trial. A Bernoulli process is a discrete time process, and so the number of trials, failures, and successes are integers. Consider the following example. Suppose we repeatedly throw a dice, and consider of 1 to be a failure. The probability of success on each trial is 5/6. The number of successes before the third failure belongs to the infinite set 0, 1, 2, 3. That number of successes is a negative binomially distributed random variable. When R equals 1, we get the probability distribution of number of successes before the first failure Saint trial, which is a geometric distribution. Over dispersed Poisson, the negative binomial distribution, especially in its alternative parameterization described above, can be used as an alternative to the Poisson distribution. It is especially useful for discrete data over an unbounded positive range whose sample variance exceeds the sample mean. In such cases, the observations are over-dispersed with respect to a Poisson distribution, for which the mean is equal to the variance. Hence, a Poisson distribution is not an appropriate model. Since the negative binomial distribution has one more parameter than the Poisson, the second parameter can be used to adjust the variance independently of the mean. See cumulants of some discrete probability distributions. An application of this is to annual counts of tropical cyclones in the North Atlantic, or to monthly to 6-monthly counts of wintertime extratropical cyclones over Europe, for which the variance is greater than the mean. In the case of modest overdispersion, this may produce substantially similar results to an overdispersed Poisson distribution. The negative binomial distribution is also commonly used to model gene expression in the form of discrete read-count data from high-throughput RNA sequencing experiments. Related distributions. The geometric distribution is a special case of the negative binomial distribution, with the negative binomial distribution is a special case of the discrete phase type distribution. The negative binomial distribution is a special case of discrete compound Poisson distribution. Poisson distribution. Consider a sequence of negative binomial random variables where the stopping parameter R goes to infinity, whereas the probability of success in each trial, P, goes to 0 in such a way as to keep the mean of the distribution constant. Denoting this mean lambda, the parameter P will be P equals lambda. Under this parametrization, the probability mass function will be now if we consider the limit is R infinity. The second factor will converge to 1, and the third to the exponent function, which is the mass function of a Poisson distributed random variable with expected value lambda. In other words, the alternatively parameterized negative binomial distribution converges to the Poisson distribution, and R controls the deviation from the Poisson. This makes the negative binomial distribution suitable as a robust alternative to the Poisson, which approaches the Poisson for large r, but which has larger variance than the Poisson for small r. Gamma Poisson mixture. The negative binomial distribution also arises as a continuous mixture of Poisson distributions where the mixing distribution of the Poisson rate is a gamma distribution. That is, we can view the negative binomial as a Poisson distribution, where lambda is itself a random variable, distributed as a gamma distribution with shape equals r and scale theta equals p, or correspondingly rate beta equals p. Formally, this means that the mass function of the negative binomial distribution can be written as because of this. The negative binomial distribution is also known as the gamma Poisson distribution. Note: the negative binomial distribution was originally derived as a limiting case of the gamma Poisson distribution. Sum of geometric distributions if y is a random variable following the negative binomial distribution with parameters r and p, and support 0, 1, 2. Then y is a sum of r independent variables following the geometric distribution with parameter 1p. As a result of the central limit theorem, y is therefore approximately normal for sufficiently large r. Furthermore, if b plus r is a random variable following the binomial distribution with parameters s plus r and 1 minus p, then in this sense, the negative binomial distribution is the inverse of the binomial distribution. The sum of independent negative binomially distributed random variables r1 and r2 with the same value for parameter p is negative binomially distributed with the same p but with r value r1 plus r2. The negative binomial distribution is infinitely divisible, i.e., if y has a negative binomial distribution, then for any positive integer n, there exist independent identically distributed random variables y1, yn whose sum has the same distribution that y has. Representation as compound Poisson distribution. The negative binomial distribution NB can be represented as a compound Poisson distribution. Let yn, n0, denote a sequence of independent and identically distributed random variables, each one having their logarithmic distribution log, with probability mass function let n be a random variable, independent of the sequence. And suppose that n has a Poisson distribution with mean lambda equals minus r lane. Then the random sum is nb distributed. Using and we obtain which is the probability generating function of the nb distribution. The following table describes 4 distributions related to the number of successes in a sequence of draws. Properties. Cumulative distribution function. The cumulative distribution function can be expressed in terms of the regularized incomplete beta function. Sampling and point estimation of p. Suppose p is unknown and an experiment is conducted where it is decided ahead of time that sampling will continue until r successes are found. A sufficient statistic for the experiment is k, the number of failures. In estimating p, the minimum variance unbiased estimator is the maximum likelihood estimator p is, but this is a biased estimate. Its inverse, r, is an unbiased estimate of 1, p. However, relation to the binomial theorem. Suppose y is a random variable with the binomial distribution with parameters n and p. Assume p plus q equals 1, with p, q greater than equals 0. Then the binomial theorem implies that using Newton's binomial theorem, this can equally be written as in which the upper bound of summation is infinite. In this case, the binomial coefficient is defined when n is a real number, instead of just a positive integer. But in our case of the binomial distribution it is 0 when k greater than n. We can then say, for example, now suppose r greater than 0 and we use a negative exponent. Then all of the terms are positive, and the term is just the probability that the number of failures before the rth success is equal to k, provided r is an integer. Now we also allow non-integer values of R. Then we have a proper negative binomial distribution, which is a generalization of the Pascal distribution, which coincides with the Pascal distribution when R happens to be a positive integer. Recall from above that the sum of independent negative binomially distributed random variables R1 and R2 with the same value for parameter p is negative binomially distributed with the same p but with R value R1 plus R2. This property persists when the definition is thus generalized, and affords a quick way to see that the negative binomial distribution is infinitely divisible. Parameter estimation. Maximum likelihood estimation. The maximum likelihood estimator only exists for samples for which the sample variance is larger than the sample mean. The likelihood function for NIID observations is from which we calculate the log likelihood function. To find the maximum, we take the partial derivatives with respect to R and P and set them equal to 0. And where is the de gamma function? Solving the first equation for P gives. Substituting this in the second equation gives. This equation cannot be solved for R in closed form. If a numerical solution is desired, an iterative technique such as Newton's method can be used. Alternatively, the expectation maximization algorithm can be used. Examples. Selling candy. Pat is required to sell candy bars to raise money for the 6th grade field trip. There are 30 houses in the neighborhood, and Pat is not supposed to return home until 5 candy bars have been sold. So the child goes door to door, selling candy bars. At each house, there is a 0.4 probability of selling 1 candy bar and a 0.6 probability of selling nothing. What's the probability of selling the last candy bar at the nth house? Selling 5 candy bars means getting 5 successes. The number of trials this takes is therefore k plus 5 equals n. The random variable we are interested in is the number of houses. So we substitute k equals n minus 5 into a neg-bean mass function and obtain the following mass function of the distribution of houses. What's the probability that Pat finishes on the 10th house? What's the probability that Pat finishes on or before reaching the 8th house? To finish on or before the 8th house, Pat must finish at the 5th, 6th, 7th, or 8th house. Sum those probabilities. What's the probability that Pat exhausts all 30 houses in the neighborhood? This can be expressed as the probability that Pat does not finish on the 5th through the 30th house. Length of hospital stay. Hospital length of stay is an example of real-world data that can be modeled well with a negative binomial distribution.